Good evening, our science students. I want to work on this flip lesson with you tonight. It's pertaining to air temperature and pressure, and these are two topics that are discussed in 6th grade. So I just want to review some important things and some extra stuff dealing with earth science. So whatever's in yellow, you want to copy down in your notebook, and the terms I will provide for you on Jupiter. All right, so air temperature is a measure of the average kinetic energy of the particles in a body of matter, a measure of how hot or cold a substance is. And it's measured in degrees Celsius, which is a C. We have degrees Fahrenheit, which is an F. We have Kelvin, which is K. And there's no degree mark for Kelvin, just a K. Looking at this diagram, we have three balloons. As you go from right to left, the temperature increases by 10. Notice that the balloon becomes bigger, so it actually expands, and the volume gets bigger. It's going to increase. Reverse, if you're going from right to left, we see that the balloon gets smaller, and the volume would decrease, and the balloon begins to contract and get smaller. Temperature versus density. We know that warm materials rise. We can see that on page 10 of the reference table under the inferred characteristics of the Earth's interior in the asthenosphere. We've seen this with the lava lamp in the classroom. All right, so warm air rises, it becomes less dense. Right? Cold air masses will sink, and that's because of its density. It's more dense than the warm air. Temperature convergence. All right, they're found on page 13 of your reference table. Each interval on the Fahrenheit scale is worth 2 degrees Fahrenheit. Each interval on the Celsius scale is worth 1 degree Celsius. The Kelvin scale is worth 1 K. And also, if you notice, there is no degree mark for Kelvin. All right, just a K. There's degree Celsius and degree Fahrenheit for temperature. All right, so let's practice one together. If the temperature is 13 degrees Celsius, we want to know what, excuse me, what the Fahrenheit is in Kelvin. All right, so go to page 13 of your reference table. All right, so we want to find Celsius, 13 degrees. We look in the middle. Our Fahrenheit's on the left, so each one's worth 1 on the Celsius scale. So this is 10, 11, that's 12, this is 13. I take this line, bring this across, and it falls between two numbers. This is 40. We know that each line's worth 2 for Fahrenheit. 42, 44, 46, 48, 50, 52, 54, 56, 58, and 60. Alright, so going back to my 13, I bring this across, it fits between these 2 points, somewhere between 54 and 56. So the median would be about 55 degrees Fahrenheit. That can work. Now I want to figure out what that is in Kelvin. Go back over here. This is 10, 11, 12, 13. I bring this line across, and it touches this line here. Each line's worth 1 Kelvin along this scale. So we have 280, 281, 282, 283, 284, 285, and then 286. So a 13 degrees Celsius mark will be similar to 55 degrees Fahrenheit and roughly 286 Kelvin. All right, let's move on to pressure. All right, the pressure due to the weight of the overlying air pushing down on any given area, gravity. Also referred to as barometric pressure. Temperature versus air pressure. We know that warm air masses will rise. We know that cold air masses would sink. And it's also due to density differences. But when an air mass rises, there is less pressure acting on the Earth's surface. Because of that, warm air masses are considered low pressures. When cold air masses sink, when they sink, there's more air in that area. So they would be considered a high air pressure. So low air pressures usually result in clouds, precipitation, almost like lousy weather. Lousy begins with an L, low pressure begins with an L, right? Lousy, low. For high air pressures, if it's colder air, but usually you have clear blue skies along with that. Second relationship is humidity. All right, so humidity is the amount of moisture in the air. As an air mass becomes more humid, air pressure decreases. This is because molecules of water vapor has a lower molecular weight than the molecules of a dry air mass. All right, so in this diagram, which is a great diagram, we have a scale with two beakers filled with air. We have dry air in one, and if you notice, there's a lot of N's, more N's than O's. And that's because nitrogen is made up of 78% of N, and then oxygen is made up of 21%. That's in our atmosphere, the air that we breathe in. However, if we add moisture to that same beaker, we must displace some nitrogens and oxygen. So if we add 3 more W's into this beaker, we must get rid of at least 2 N's for every 1 O. Because of this, water has a lower molecular weight than dry air. Right? Nitrogen and oxygen combined can give you around 60, and that's the 60 relative molecular weights of dry air. So more moisture, less weight. In this case, less weight will represent low pressure. And that goes along with rising air masses too. All right, last relationship is altitude. Now on page 14 would display this in great detail. All right, your middle graph is your air pressure graph. All right, so here it says gravity always pushes materials downward. As a result, there is more air pressure at sea level than at higher elevations. All right, so since gravity is always pulling things down, on this graph here we have at sea level, my atmosphere is one atmosphere for air pressure. The higher you go in the atmosphere, my air pressure lessens. All right, it goes from like 1.0 almost to 0 as I get all the way up here in the thermosphere. So as altitude increases, air pressure decreases. That's an indirect relationship. Last thing I want to mention is the conversions for pressure. All right, pressure conversions are found on page 13 of your ESRT. Each interval on the millibar scale is worth 1 MB, and each interval on the inches is worth 0.01 inches of Hg. Let's practice one together. Identify the pressure in millibars when the actual air pressure is 29.48 inches of Hg. All right, so let's go to our inches, our pressure. All right, notice on the left-hand side it's in millibars, MB. Each line is worth 1. On the right side we have inches of Hg. Each line here is worth 0.01. If you go to the bottom of the same conversion, they tell you that Hg is also mercury. Alright, so we want to find 29.48. So here, 29.40, 29.41, 0.42, 0.43, 0.44, 0.45, 0.46, 0.47, 0.48. So I bring this across, and it kind of falls somewhere between these two numbers. So we know each one's worth 1, right? So we have 996, next one 997, 998, 999, 1000. So that would fit somewhere between the 998 and 999. So a number in the middle can work. So 998.5 millibars can work for this answer. Alright, so that will conclude this lesson. Tomorrow, please be ready for smart response and activities pertaining to temperature and pressure. Have a good night.